Hi, everyone. Thank you for attending this talk. We're going to talk about a new technology that we invented, a new novel technique that basically will change what everyone here will probably know about how we're going to detect attacks and how we're incorporating the ability to learn how open source libraries actually behaves around the world and taking that to a new ability to detect and block attack. So before we begin, I'll quickly introduce myself. I'm Gal, I'm the co-founder and CTO of Oligo Security. I've been building and breaking software ever since I remember myself. And in the past decade, I was hunting for 0 days for my living, basically finding 0 days in the biggest application in the world, until one day I hacked Instagram. Why? Mainly because they're Instagram. But the really interesting part was that all I needed was one vulnerability in one open source package in order to take down Instagram globally, every app around the world. And for us, it was like, at the beginning, quite surprising. There's only one vulnerability in one package out of tens of thousands of open sources that Instagram were using. How come all I need is just one vulnerability in order to do that? And of course, all of that was a year before Log4Shell, and I kind of like, told you so. But this moment was an epiphany moment for us. We decided to stop everything we do and just go and build and invent a new technology to deal with this type of threats. But in order to understand what we've done and how we've done it, we need to understand the history a little bit before. And in order to understand the history, let's understand how we tried along the history to secure applications, secure open sources. And just for set straight, when I'm talking about application, it doesn't matter if you build them or bought them or deploy them or even install them. In the end, it's pieces of code that combines together to create a logic. 90% of the modern application is composed of open source projects. In the end, we don't want to invent a parser every time we want to parse an image, right? And that's why today applications are those, aggregation of open sources, SBOMs. The world has started giving it a name after really big two hacks, SolarWinds and Log4Shell. And this is how we ended up starting to talk about applications in general. It doesn't matter if it's running on your endpoint, server, microservices, Kubernetes, or whatever. In the end, it's software running on infra. And the first early days, I guess you all here are familiar with the whole shift-left approach, started in 1990 by IBM, when the easy, most straightforward way was just, OK, let's look for all of the risk in the code itself, whether it's a legal risk like licenses or malware or vulnerability. And this approach was really great back then in 1990 when my grandma was still coding. But from that era, the world has changed a little bit, right? We move a lot more code. And these approaches became very problematic. Why? Because when we look at actual ingredients, the pieces of code, when we scan repo, we see all of the theoretical risk. And it might sound very easy and straightforward, but let's take this example. I have a smoothie, and I want to know if I'm allergic to nuts. But when I go and I look at the ingredients, I see there's a strawberry that might proceed in a gluten-free factory next to eggs that might contain traces of nuts that might and might and might and might. When there's too many mights, you don't really know, am I fucking allergic to nuts or not, right? And this is all I want to know. And this approach became very ineffective, very noisy. We're talking about hundreds to millions of vulnerabilities potentially impacting an organization. And of course, when you're just scanning stuff, scanning repos, scanning clouds, you're not dealing with the real issue, which is when one of those vulnerabilities actually become real, an attacker leverage it in order to breach your application. And those approaches, by just scanning now and then the repos or the workloads, are not really dealing with the actual detection or prevention of those attacks. And again, the world has changed a little bit from 1990. We're talking about pushing a lot more code, a lot faster to production, distributed application, AI. I know you all waited for this buzzword, but LLM helps us write a lot more code, a lot faster, and it is using open source software as well. So this problem will just keep on rising. But this is just the way that we look at it from the actual code itself, actually scanning. And this is where the world understood there's a need to shift right back to actually protecting from attack. And now let's talk about that. So the first wave of trying to protect application was actually the same people that invented the shift left. Fortify, the first ever company, started with two approaches. One was scanning the repos in order to find vulnerabilities. The second one was to actually detect attacks in real time. And the first approach that started was RASP, Runtime Application Self-Protection. How many of you have heard about this acronym before? And I bet that you've heard about it. It wasn't that a good example for how things are done, because this approach completely failed. It was due to really big two main reasons. One is stability. When you're crashing an app and you're losing the credibility, and of course, if we're talking about real production environment, of course, no one will give you a chance to do something, or even if you didn't crash the app, but you're adding so much overhead in a manner that it's so expensive to run your tool, it's actually doing what it wasn't intended to do, and it was simply undeployable. So this first approach was basically involved taking your developers to push code to monitor your production environment. Doesn't matter if it's SDKs or Java agent, the fact that it's being done through user mode, what's called user mode instrumentation was the part that really made this approach failed. And then we saw the second wave of trying to protect application, starting from network security. Again, I'm a bit biased. I grew up in Checkpoint. Everything we do is firewall. But the main goal of the first firewall was to protect the business application. But firewall was actually just setting the perimeter. And then we had the amazing invention of the WAF, Web Application Firewall, right? Much more tailor-made to application, but still on the network layer. And this is why this is a great approach, a great example, but this approach is also protecting the network and not the application itself. And another way to look at it is what we all know as antiviruses, EDRs. Back then when we started looking about what a process is doing, we basically looked for post-exploitation technique. Someone dropped a shell, someone is reading from etc plus WD, someone is already there doing bad stuff, and we're trying to catch the attacker after the fact. Those two approaches did a great job protecting the perimeter, as we call it, network or host-based attacks, but no one was actually dealing with the real problem, the in-app application attacks, and that's why log4shell happened, right? We had any tool in the market that, again, deal with network security or host-based security, EDRs, and still log4shell happened. And this is the great testament that playing around the app and not being inside where it actually happening, the attacks themselves, it's what's keeping those approaches behind. And this is where we understood that we need to create a new approach that will be easily deployed like the one that you all saw, but that will monitor applications and not processes. This is a very huge difference to monitor your Java, your Python, your Go, your Node, versus just monitoring a whole process and not being even aware to the underlying technology. And this is what we call the ADR. But before we deep dive and understand how ADR is built, we need to understand how is it even possible. We're just talking about the ability to monitor every type of application without the need to access your code, without the need for your developers, and without requiring high privileges. Just plug and play and start observing in a level that wasn't possible before. And the most important thing is that we do all of that without being intrusive. So we all discussed about RASP and the fact that RASP is dead, but the fact that RASP didn't succeed, it doesn't mean that there isn't a market need for that solution. And this is why we believe that random application, it's not dead, and it just requires a new technology that can actually make it happen. So all we need is just to find a better technology that can seamlessly in a frictionless way ensure that we do not disrupt any performance of the application, and we do not introduce any developer friction. Second, it should provide a comprehensive attack coverage, monitoring the entire host, not just the application itself. And it should be easily deployed and maintained. And of course, most importantly, it should be safe and stable. So, sounds too good to be true, right? So, it is too good to be true, and it is thanks to this amazing technology, eBPF. I don't know if all of you have heard this buzzword before. or if you're familiar with eBPF, but for us, we believe eBPF, it's what is actually needed in order to answer all of those questions. And let's talk about the role of eBPF in today's AppSec and explain why it's much more than just a buzzword. So, what does eBPF mean? How many of you are familiar with eBPF? Heard about the term? Google guys, of course. I'll do a quick overview, but this is an amazing technology that actually exists in the Linux kernel from 1990. Actually, in Checkpoint, in the first firewall, we used it. It starts from a BPF, Berkeley Packet Filter. It started back in the 90s. Basically, as the name indicates, packet filtering. It was mainly used for amazing technology you probably all know of, Wireshark or TCP dump. And from those moments, people started adding more and more and more code, and this is why the E goes for the extended, and we basically created a whole new programming language in the kernel that now can extend the capabilities of the kernel in a safe way, completely making kernel driver useless. And the beauty is that now you don't need to reboot the system, you don't need to rerun your app, you can just start observing anything while is it running, and the most important thing is that this technology is safe by design. So what does it mean? It means that eBPF has a component, it's called the eBPF verifier, which basically asserts every code that you want to load to the eBPF layer and make sure it's not doing anything that it shouldn't do in terms of the restrictions of eBPF. And this is the restriction. It should not access invalid memory. It should not allow infinite loops, and it should not hang the kernel, block the kernel, which means in the overall, the verifier just makes sure that eBPF programs follow the best security guardrails for your Linux, and simply to put it, it's just there to make sure it won't crash. So I know how many of you heard or impacted or saw it, but CrowdStrike outage probably is the best reminder for all of us in here that kernel driver can be a big problem. And this was the biggest IT outage in history, and it was all due to a kernel driver bug. And this is where eBPF is very, very different in this approach. Even if you want, you cannot harm the system. And one of the best gurus in the world, Brandon Gregg, did a whole study only on that. It's called No More Blue Fridays, basically comparing the way that we use kernel drivers today with comparison to eBPF. So why should we use eBPF? First of all, because it's everywhere. It's in your Linux machine. You can just go, grab, start, observe any application that you want, hook a specific place in OS, gain visibility, and zoom in a way that wasn't possible before. You don't need to install anything. You don't need to risk your application in crashing it. And of course, the application can already be running. You don't need to deal with it or rerun it or do anything special. And the beauty is that everything, it's super efficient. eBPF implemented new technologies such as JIT, just-in-time compiler, that you probably all heard of from Java or Node or new high-level languages. And the beauty is that we are already in the kernel. So there is no need to do context switches, which means we are already in line, and that's why this approach is super battle-tested, that even the biggest companies in the world, like Google, they took it for security monitoring. Meta just swallowed the people that invented it and took it to load balancing and networking, and Netflix used one of the biggest gurus, Brandon Gregg, in order to create a performance monitoring in scale on the biggest AWS cloud environment that was out there. So how all of that magic is actually possible is due to this ability of eBPF to just observe everything. When we talk about eBPF, there are 120K probes all over the system. Just imagine you can, like, how crazy is this that you have 120,000 different places in your Linux machine to just observe what your application is doing. And this ability to observe everything, like system call or IO events or networking, UDP, TCP, everything that you should have think of, it already had a probe in it. And eBPF, it's basically an event-based language. You're registering to some event that happens, and you're running your BPF code. And in that manner, you can start observing the system. So in order to understand how can eBPF be used for security, the first question that we need to ask ourselves, what eBPF is actually accessible? What is accessible to an eBPF program? eBPF do exist for a lot of time, but it became mature only in the recent years. And needless to say, it will not replace kernel drivers completely, but it does enable stuff that wasn't possible before. And this is why it's important to understand how the world has been using this amazing technology. So this is an example for two very simple, straightforward example of using eBPF. One of them, it's the system call layer, which uses trace point. It's basically the ability to hook to every system call in the system. Doesn't matter if it's the beginning of the system call, the end of the system call. You can just tap into it and add your own logic. And the most important thing is that attackers cannot avoid doing system calls. They have to. This is the way for your user mode to communicate with the kernel mode. And that's why a lot of security products will use the system call layer in order to observe and look for attacks. And the second example, a USDT, just to show you how dynamic it is basically what is called user-defined, user-statically defined tracing, which basically allow you to assert hooks inside the application layer. It is only for several languages that do support it. You do need symbols, but just the ability to hook inside is just giving you the ability to understand, wow, you can hook even inside a running context of an app, which is something that isn't straightforward. So if I didn't surprise you enough with eBPF, now I'm going to show you that you can also run eBPF on your network interface card. It's a small, different card on your endpoint that it's usually only used for network, but it's running Linux, and that's why it has eBPF, and that's why it's actually being used also in that manner. Cloudflare, it's one of the biggest users of XDP, Express Data Path. This is the name of that feature. And of course, it can do everything from packet inspection to packet manipulation and even DDoS protection. And only recently, actually, Cloudflare prevented the largest DDoS attack in history, all due to this amazing technology. And how? They just dropped the packets before they even reached the Linux networking stack. So just imagine how efficient it is when you can just taking down the packet even before your machine is starting to parse it and to create a lot of resource consumption, which is what DDoS attack is all about. And of course, that sounds really, really cool and amazing. So why not use it everywhere? Because it is fucking hard, right? You're writing kernel code. You need to be proficient in Linux. You are running inside the kernel itself, and you're using eBPF, so you need to be aware to all of the eBPF restriction. There isn't much out there. There are amazing communities out there, but it's not that straightforward to start using eBPF. Even if you do use eBPF, it doesn't mean that you are writing a production-grade program, right? I can monitor every system call, but if I slow down the system, I didn't do anything, right? And of course, the fact that it was only being used for performance monitoring up until now, it means that it's not a security tool. Brandon Gregg has this famous saying, performance tools are not security tools, and it's a whole different layer. And I think the best testament, it's this funny picture from strace. strace, it's the oldest a component in the Linux that was built to monitor a system call for performance monitoring, and it has a bug from 10 years ago that says, oh, when you trace a process, it runs slowly. So this is exactly the example why performance monitoring tools were never meant to do security. So let's focus on the latest trend, how eBPF and security became that prominent. And we can all look at some of the examples, Falco by Sysdig, or Tetragon by Isovalent, or Aqua by Tracy. And of course, these guys got the trend, and there's a reason for it. They took it for their host intrusion detection system capabilities. But again, one of the most unique things that happened recently in eBPF is the introduction of KRSI, Kernel Runtime Security Instrumentation. It's basically a new technology that was added by Google to eBPF, which basically combined the amazing capability of SE Linux, which is one of the most dominant tools in Linux to do enforcing and security. It's basically combined the underlying mechanism of this technology, the LSM level, Linux security modules. It's basically 200 hooks inside your kernel that are only designated for security. But the real innovation that changed everything, it's now not only observe the system, but actually being able to proactively do stuff, like being able to block an attack or access memory, stuff that you couldn't do before. And this amazing technology, it's what actually enables eBPF to become a new, different animal that can actually block attacks and detect in real time. So in order to understand what eBPF actually means, this is a small program of eBPF that can count every system call. You can see how easy it is. You can write a C program and compile it with BCC, which is like GCC, the compiler, but only for BPF. So it's called BCC. And it's how easy and straightforward it is to start observing the kernel within a second. You can also, again, with XTP, count every network packet. But the real cool stuff is that you can start observing application logic even before it happened. This is an example of how you can just sniff a raw HTTP packet before it actually gets even executed, see the parameters of your Firefox packet, and decide whether you allow it or not. Just imagine how cool it is. It can be like WAF on steroids, 20 times better, but this is just a tiny example. So we got to the most interesting part, how we're taking all of that and being able to detect zero-day attacks. And I know this sounds too good to be true, right? Like every tool claims that you can detect those attacks, but of course, needless to say, no tool in the world was ever been able to deal with 0 days, so theoretically no one can. But I'm here to change this assumption, and in order to do that, let's just talk about a real 0 day that just happened recently, the XZ backdoor attack that was only discovered in latest March. This attack resulted in several backdoored Linux distribution. It means that the attackers here basically breached Linux itself and almost got to the main distributions. It was a very complicated attack that took for years, that they basically poisoned the CI of GitHub, and through that, using a binary test file, actually being able to infect and poison the XZ utils, a very famous package in the Linux, and infected with the backdoor. And of course, this of course raised the question, could we actually detect it in real time? And of course, when we talk about XZ backdoor, the world got crazy, and everyone was starting to talk about it. But in the end, we all got very lucky because performance engineer for Microsoft that saw that he has 0.5 seconds overhead decided to benchmark his SSH connection and found this attack. So we were lucky. But when I mean we were lucky, I mean just think about how unlucky we are and how many out there that we can't even find. And again, we cannot depend on performance engineers to save us, right? And this is where I'm still concerned about all of the backdoors that we still don't know about. But I'm here to give you another angle. Of course, every security company in the world claimed they could have caught it afterwards. But when I mean detecting it, I mean how you can actually detect this attack even when it was a 0 day, even without knowing about it, even without having a CVE in order to identify where it is. So in order to understand that, I think what was really missing in that approach was the fact that if you do have the application context, it's not that hard to do it. If we understand what actually is happening there, it's basically an SSHD doing SSH to a machine that was manipulated by the attackers, and they added a hidden system command that can run arbitrary code. But they did it by abusing one of their libraries, the libelzma library, which is a compression library that, as you all guess, should only do compression of files. And suddenly it executes code. And this is where this approach really is changing the game, as exe should never call the system command. Never. Not in any real-world use case. It's that simple. So we actually created an example of this attack. And basically, what we've done is to show how we can handle with this attack even before we even knew about it. And of course, those attacks just reminds us how, and when there is an incident, the best thing we can do as an organization is just run and look for where we have these vulnerable packages and start to remove them from the system, and how much time does it take, and why it always happened on the weekends, on holidays. I don't know why attackers are doing it, but it always catches us with our pants down, and this is why exactly we invented Oligo. Oligo is the world-first knowledge base of how open source should behave. We basically invented the ability to monitor those same open source libraries that we all use for enough environment at enough time to have the data, the network effect, the crowd wisdom to tell you how this piece of code is being used around the world, and not only at your code. And then in real time, we can actually detect any deviation from this base profile. We can detect and even prevent those attacks. And we don't care about no CVE. We care that a parser should only parse file. We care that NumPy should only do mathematical computation. And when you look at that level, when you take PyYAML, which is a famous YAML parser, and you actually observe it around the world, you can see that all it's doing is actually talking to the file system, as it should be. So just by narrowing down on a specific open source, rather than trying to learn the whole application, which is a lot more complex, a lot more broad, now you have a new approach that can catch the act of the exploit itself. When PyYAML talks to the network, it means right now you're getting exploited. We don't need to wait for it, oh, to which IP it was talking, or which bad action did it did. We're catching the act of the exploit itself. And this is the beauty that we've been doing it for years, so we already have thousands of open sources that we know how they should behave, and only based on this essence, we can detect any attack that is happening on them. So let's take the exe example. We have an attack here that only by leveraging actually a really great research that done by Google that actually took this exe backdoor, Anthony Wims, and basically replaced the private key of the attacker with its own private key, which means now he can control the backdoor and mimic the attack one by one. So this is exactly what we did. We just mimic the attack, and then you can see in Oligo, I'll show it in a second, how we can actually catch this anomalous behavior even without being aware. Again, due to the fact that we are monitoring the libraries themselves, and that library level monitoring showed that this libelzma should never execute code. Basically what we did in order to replicate the attack is to run in this SSHD, again, activate the attack with our own control private key, and then while we can actually connect to the machine, we can trigger the attack to create this abnormal system function execution that we can either catch or even block. So I'll just show it. Cool. So you can see in front of you a real example. You can see here that the exe package is still dormant. We still haven't run it. But now we're going to actually, on the machine, on one hand, have the attacker actually running the same backdoor with a command that will create a file on the victim server as root. You can see on the right side that the attack was successfully happening. This is, again, using the same exe backdoor that was infecting the whole world. And then you can see right away in Oligo how, even without being aware to this type of attack, the liblzma library suddenly did an abnormal behavior, which created a suspicious process. And now Oligo could have coded down to which function did what, which is allowed or not allowed, and with that, actually being able to detect this attack as a 0-day. So just to conclude everything we saw, we all deal with CVEs, which are risks that we are aware of, but there are a lot of risks which are not aware of. 0 days is one example. Shadow vulnerabilities is an example that we did a huge lecture about it. Just the concept of like a lot of libraries just get misused or not following best practices, or the maintainer decides this is not a bug, and we ended up in a risk that doesn't even get a CVE. And that's why runtime solution is required in order to detect those attacks. We cannot only count on those static approaches that scans now and then for vulnerabilities. This new approach is basically a whole new mitigation that we invented. Just imagine, just like Google Chrome sandbox each and every tab, now you can sandbox each and every open source library, which means it's changing the way that attackers can exploit vulnerabilities. And of course, the fact that we can detect attacks by only observing the library behavior and its deviation, it allows us to catch attacks even without any CVE required. So thank you very much, everyone. Of course, this was only one example. We had many more of examples of real attacks out there in the world. This is from another lecture that we call Shadow in AI. We basically hacked PyTorch, TensorFlow, Ollama, every AI framework that you all think of or used, all by proving that they misuse one of the open source libraries, and that's why those attack doesn't even have a CVE assigned. And that's why we all think it should be a community effort to try to deal with those type of risks. So again, thank you very much, everyone. If you have any questions, I'm here, and thank you for attending this talk. I think we don't have time, but if there's any question, I can answer something. Yep.
So you said you think this should be an open community effort. Is Oligo an open source agent that's running an open source eBPF agent?
So when I meant, he asked about the community effort, I meant that shadow vulnerabilities themselves, we actually created a whole database of all of the shadow vulnerabilities we know of, and we created actually technologies to look for them in scale. And of course, this is what we mean should be a community effort, and that's why we created a whole website only for that, and we urge the community to add more and more examples into it. Okay, cool. Thank you, everyone.